For those of you if you have internet connection problem, please go to the setting and then set your video receiving to 720, but your sending over there, just click on audio, sending audio only. All right. Okay, so we're gonna start with our lesson for today. Our lesson today is going to go back into 5.2 damping and also resonance. All right, so damping and resonance, I'm going to start with showing you guys a video simulation over here. So I'm going to let this oscillate by itself. All right, so the damping, if there is no damping, let me show you here. Okay, if there is no damping, and let's just say I adjust this, consider no and better. All right. When I put it at slow motion, you would notice that the amplitude of all these crests, all right, it's actually the same amplitude. All right. Main reason here is because over here at the bottom part, there is no damping. In ideal cases, the amplitude starting from the source of the vibration, all right, the amplitude should remain the same throughout the whole entire wave. But then one thing that we notice that, as I already previously mentioned to you, in real life situation, there's no such thing as a perfect and ideal situation. All right, so there is definitely something that is lacking. Okay, wave is actually a transfer of energy without transferring matter. Transferring of energy here, just a quick recap for all of you. Here, this green color particle is actually being forced to oscillate, to vibrate. So it actually causes a disturbance throughout the whole entire line, causing the energy to actually transfer. When it moves up, it has maximum gravitational potential energy, and when it moves, it has kinetic energy. So this energy is being transferred from this position here, all right, on the part that my cursor is located, all the way towards the right. So energy is being transferred. Okay, but this case, you will notice that the green color particle just vibrate up and down. All right, the vibration of the particle just vibrates up and down. So wave, to recap back, wave is a transfer of energy without transferring the particle or the matter. So in real life situation, we know that conservation of energy cannot be created, it cannot be destroyed. This sentence, this conservation of energy will keep on repeating in almost every single possible chapters in physics. So over here, all right, over here, what happens is, in real life situation, not all the energy is going to get transferred. It's going to get lost in terms of the energy might have went to overcome some frictions with the surrounding. It might have collision with the air particles surrounding. So in real life situation, the wave, the amplitude will actually change as it moves away from the source of the vibration. So over here, I'm going to increase the amplitude so that you guys can see it more obvious. All right, you would notice that this wave is slowly moving downwards, the amplitude. Watch again, when it goes up, as it moves towards the right, the amplitude starts to decrease. Okay, and this decrease in amplitude is what we know as damping. All right, in wave, when the amplitude is reducing, all right, as it goes further, that is what we know as damping. So as if there's no damping at all, the amplitude is the same, maximum all the way. But if there is damping, energy loss, all right, you can see that the wave is slowly, the amplitude is slowly reducing. Okay, so this is actually what we called it as a damping situation. Okay, so let's go back to the notes that we have. Those of you who just answered, please make sure that you either open up this PowerPoint slides that I've already sent into the respective groups already just now. Okay, so this is actually in the Form 4 textbook. So Form 4s, please make sure you open up your textbook, or if you already printed out, you can directly write on top of it. Okay, now damping and resonance, I would want to ask you guys to take concern and take attention to this. So Form 4, please do take attention. Form 5 also. Previously, damping and resonance part under the subtopic of wave first subtopic. All right, so last time it was actually 1.1 because wave last time was in form 5. But right now, since it's in form 4, and they took out and put damping and resonance as a subtopic by itself. So when they take out damping and resonance as a subtopic by itself, which means they are placing this as an important subtopic already. So when they place it as an important subtopic, which means that there are possibility that the question might come out, all right, either during the module pintas or probably at the trials or SPM level, all right, because why they are already considered it as something important, not to be in part of inside one of the sub question or sub topic, but this is a subtopic of its own already. All right, so which means they are saying that damping and resonance is something that the students should learn and should understand and not to skip through it. All right, so an oscillating system that is placed and left to oscillate without an action of external force, it will vibrate at its natural frequency. All right, so natural frequency, this is a definition, so highlight this definition. Okay, when an oscillating system is displaced and left to oscillate without an action of external force, it will oscillate at its natural frequency. So over here, that is the first definition, okay? And this is a picture of a displacement time graph for damping. All right, this is a displacement time graph for damping. This one, you can see that the amplitude decreases, all right, as time after a certain period of oscillation. All right, so here you can see that initially, all right, the amplitude is A1, and then after that becomes A2, A3, and A4. Now, please do put a remark. You need to learn how to draw this graph. I'll teach you how to draw this graph in a short while. All right, so which means make sure you have your blank piece of paper or your pen, and make sure you have your ruler and your eraser with you. All right, in a short while, I'll discuss this with you guys, how to draw this graph. Now, the amplitude, you would notice that A1 has the maximum amplitude, then it reduces to A2 and then proceed to A3 and finally A4. All right, the amplitude decreases. So here in the textbook, it says that the oscillation of a simple pendulum experiences a significant external damping. All right, but insignificant internal damping. For the vibration of a spring, both external and internal damping happen significantly. So what does this mean? In a short while, again, I will explain this further. Now, an oscillation with its amplitude decreasing with time shows that the system actually experienced a gradual loss of energy. So one thing that I want to relate is, in terms of wave, all right, if the amplitude decreases, or I should say amplitude affects, all right, amplitude will affect the energy level. All right, amplitude will affect the energy level, energy of the wave. Okay, amplitude will affect the energy of the wave. So if the amplitude decreases, it will actually experience a gradual of energy loss, which means energy decreases as well. All right, and finally, it will keep on decreasing until the oscillation stops. All right, it is like when you go to the playground, all right, you know the swing part, you push the swing, all right, when you push the swing, you are the external force. Okay, so it's not considered as vibrating at its natural frequency. But when you push the string, all right, you and it's not strings, swing. Sorry, when you push the swing and there's no one sitting on the swing will actually slowly stops. All right, why? Because it experienced damping. Now, where does this damping comes from? The damping will come from the internal damping. All right, and it will finally stops if there's no wind and you don't go and push the swing again. All right, so there's two types of damping situation. Okay, first is known as external. External means outside. The source of the damping is actually from outside the environment. So the oscillating system loses energy to overcome friction or air resistance. Okay, if a spring, All right, if a spring is actually placed on top of a floor, all right, and you let the spring oscillate, it will slowly stop because it has friction with the floor. But if, let's just say, if the spring is vertically, all right, it will actually vibrate up and down, and it will slowly slows down because it has to overcome air resistance. All right, so that is the difference between friction and air resistance. Friction is when it's horizontal. Air resistance means that it's not in contact with any other surface, it is just only in contact with the surrounding air. All right, so that's external damping. Internal damping, all right, the oscillating system loses energy because of the stretching and the compression of the vibrating particles in the system. Inside a spring, right, to recall you guys back, a spring is a solid material. Solid material means there are molecules closely packed to form the spring. So when you oscillate a spring, you are actually causing the particle to stretch and to compress. So whenever it stretches and compresses, it will have to do work, and the system will have to overcome the energy. All right, to overcome the work, so it will lose its energy. Okay, so external damping is either from the frictional force or the air resistance. Internal damping is due to loss of energy because of the stretching and compression of the vibrating particles in the system. Okay, so please do take note on external and internal damping. Now, what is the definition for damping? So they didn't highlight this. I'm going to highlight this for you. Damping's definition is the reduction in amplitude in an oscillating system due to loss of energy. Right? The reduction in amplitude in an oscillating system due to loss of energy. This is the definition for damping. So during damping, the oscillating frequency remains constant while the oscillating amplitude decreases. Okay, so in a short while before we start discussing regarding reflection of wave, I will tell you what is the cause, all right? What, when we change something, what is the responding effect of it? Okay, so I already started with one, which is the amplitude and the effect of energy. Okay, next is the effect of damping can be overcome by applying a periodic external force on the oscillating system. All right, if the swing, back to the situation of the swing. Okay, back to the situation of the playground swing, for example, saying it already. Okay, let's just say this situation of the swing, we actually let this swing to oscillate to and fro. Okay, you push it one time with no one sitting on it. All right, realistic situation, when you push the swing, it will actually start to move back and forth, and then it will slowly slow down. So if you want to let it continue swinging, obviously what you have to do is you have to push the swing some more. So when you push the swing, a person pushes the swing, the person is actually the external force. All right, the person is actually external force. Now, if let's just say for a situation, no one is actually pushing the swing, okay, but what happened here is there is wind blowing. All right, there is wind blowing, and then the swing starts to move. All right, when this move, and it will move not based on the wind, all right, it will actually move at its natural frequency. When the wind stops, if the swing continues to move initially, that is the natural frequency. Okay, but obviously one thing, damping will definitely happen because of the chain that is connecting the swing to the rest of the swing structure. Okay, go and see. Okay, so here this is actually what you have to understand. If you initially displace the swing and then it starts to move by its own first, that is the natural frequency when you take off the external force. If you want to continue or let it swing back and forth, then you have to use your external force, which is your hand. You have to push the swing so that it continue on swinging back and forth. All right, so that is known as the external force. Okay, like for example, if you were to remember when you guys did the pendulum experiment for your paper 3, okay, so you tied, there's a plywood over there and then there's a pendulum. When you haven't when you haven't start doing the experiment, you would notice that the pendulum will start swinging back and forth already. All right, why? Because the wind is blowing it. But once the wind stops, the pendulum will continue on to move for a while at the same amplitude. That is the natural frequency of the pendulum. Okay, but after, if the fan is being switched off, the pendulum, you would notice that it will start to vibrate even less and less, and then finally you will stop moving at immediately. All right, that is the situation that we call as damping. Okay, so this damping, in experiment wise, this damping comes from internal. All right, it comes from internal and also external, depending which is more. Okay, they won't ask you in the pendulum experiment, would the damping be external damping or internal damping. No, they won't ask this kind of question. The most they will ask is where does external damping come from, where does internal damping come from. Okay, they won't ask which is more, which is less. Don't worry about that. You just have to understand what is the meaning of external damping, what is the meaning of internal damping. That is sufficient. Okay, now let's see. Okay, so before I end regarding damping, I'm going to start teaching you guys how to draw a damping graph. Okay, so when I'm going to teach you guys how to draw the damping graph, I hope that you have paper, pen, ruler, pen or pencil. Pencil is preferable. Ruler, eraser. All right, so get it ready. In a short while, I'll start. Okay, I use this better. Okay, are you guys ready? Please do take note, use a ruler to draw. I'm using my drawing pad, so I can't really use a ruler. All right, so what you have to do is, if you have the line paper with you, then it would be even better. If you don't have, then try to use the ruler to draw it nicely, okay? So I'm gonna draw the y-axis first. So I'm just gonna draw this as my y-axis, and the title for y-axis is actually amplitude. And amplitude, depending if it's they asking us to sketch, then I'm just gonna write meter. Okay. Then after that, I will try to skip 2 lines. All right, this is where my x-axis is going to be. And I'm going to write this as time. Second. Okay, so what I'm going to do next, if you guys are okay, I'm going to write this as, I'm going to consider this as my amplitude. Let's just say I'm just going to write as 10. That's my maximum amplitude. Down here will be -10. Here 0. Depending on the question. If the question didn't say anything, then you probably write A and -A. Okay, depending on the question. Now, then after that, can you please use your ruler every 0.5 centimeter? Put a marker over there. So 0.5 centimeter, put a marker, 1 centimeter, put a marker, 1.5, 2, 2.5, 3, 3.5, 4. So I'm just going to label down here. This one is actually the period. So this is half t over 2. This is t. 3 over 2. And then here is 2t. Then after that will be 4. Not 4, sorry. Should be 5. 5t over 2. 3t. 7t over 2. And then 4t. T here represents period. Okay? Are you guys alright? Hope okay, yeah? Now, what you're going to do here is, alright, from this amplitude area, alright, starting from this amplitude area, draw a dotted line, a curving dotted line, alright, as though that is exponentially curving down. Okay, draw an exponential dotted line over there. I'm going to use another color so that you guys can see. Okay. And don't let the dotted line touch the x-axis. I repeat, do not let the dotted line touch the x-axis. Okay? Then at the top part, try to draw the similar dotted line that reflects from the bottom. All right, just try your best to draw so that the top and the bottom looks the same. Please, do learn how to draw this. If I were to stop and teach you guys how to draw this, then your pandai meaning means in SPM, in trials, in end of the year, it is actually important for you to learn this. Because, as I said, I always refer to DSKP before I actually start teaching you guys. And I'm a bit the perfectionist whenever I draw something related as a graph. Okay. All right. Now I'm going to be drawing the actual graph for the wave already. So I'm going to start from here. All right. You can start from 0. You can start from the top. So it's my habit to start from 0. So my complete oscillation, I need to have at least 3 complete oscillation of wave. All right. So I need to have 3 complete wave minimum on my graph. So that's why I asked you guys to draw T, 2T, 3T. All right. So what I'm gonna do here is do watch how I draw first, okay. I know my drawing is going to be a bit chatted already. So from here, Form 5, you guys know how to draw the sinusoidal wave, so please do draw the sinusoidal wave. All right, so from here, going up, come down. Try to draw it smoother. If I draw freehand in school, it will be much more better, but using a drawing pad, very challenging. You can touch the dotted line, no problem. Like this. Okay. So this is actually how you draw a damping graph. You need to make sure that the amplitude decreases, all right? And there's at least 3 waves inside there. Okay? Now, while you're drawing this, I'm going to open up a new later on in the IC. If I'm not wrong, I have a question that asks you guys to draw also. So in terms of damping, they will only ask you about conceptual question, and they will actually ask you what's the definition of damping, and then ask you to draw this particular damping graph. Okay, so there's not much of a calculation for damping. Okay, so if you guys are all right, I'm going to proceed to resonance right now. Okay, any problems with the graph?
No problem, sir.
All right, good. Okay. Now, let's look next. We're going to go into resonance right now. Okay. Just now, damping is whereby we see due to external reasons or internal reasons, the wave actually slows down. Okay. But for resonance, Okay, resonance means we force something to oscillate. Like for example, the pendulum question again. If there's no wind, the pendulum in the experiment, let's see. Okay, if there's no wind in the pendulum experiment, okay, the pendulum will actually hang steadily, all right, vertically. But if there is a wind being coming and pushing this pendulum, or we take this pendulum and we purposely go and displace, we move the pendulum, all right, that is actually called external force. So when we want to force something to move, and then if it moves at its natural frequency, okay, then that is actually what we know as resonance. So let's look at the definition of resonance. Okay, so according to your textbook, when a periodic force, why suddenly like this? When a periodic force is applied to an oscillating system in its natural frequency, the oscillating system is said to be in resonance. So the key words over here is periodic force applied to an oscillating system. Okay, and it actually oscillates at its natural frequency, the system is actually said to be at resonance. Okay, so here the resonance system will oscillate at its maximum amplitude. Okay, so during resonance, what two keywords? Number one, it will oscillate at its natural frequency. Number two, it will oscillate at its maximum amplitude. All right, which means that it will vary the energy of the pendulum, right? It will be vibrating and it's actually moving at its most maximum amplitude for it. Okay, so let's go to the next one. Okay, there is good effect and also there's bad effect for resonance. Okay, so resonance good effect number one is the tuner in the radio or television. Okay, this is obviously the old syllabus 10 years ago lah, okay, when we don't have Spotify or whatever, right? Whenever we want to listen to a radio last time, we actually have to turn the dial on the radio box, all right, or the television. We have to keep on pressing for the right frequency, all right. So when we actually use this is actually whereby the circuit in the turner is adjusted so that resonance is achieved. Like for example, if you want to listen to Mix FM, example 95.8, all right, 95.8, this is actually megahertz, this is the frequency. So this is the frequency at Klang Valley area that Hits FM is actually sending out its signal. So if you are located at Klang Valley, you just have to use your handphone or you use your TV or you use the car radio. You change the dial to 95.8, which means that you are actually trying to change the circuit inside the radio station, inside the your car radio or your handphone frequency, so that it is in resonance with Hits FM's frequency. All right. So at the frequency transmitted by a particular station is selected. So once you turn into 95.8, a very strong electrical signal is being produced. So if in Klang Valley it's 95.8, let's just say right now I'm in Negeri Sembilan. So when I'm in Negeri Sembilan and I try to find 95.8, definitely I cannot get Hits FM anymore. I'll get some other languages radio station. Okay, so why? Because 95.8 in Negeri Sembilan, it's another radio station's frequency. Okay, so resonance must be achieved when I tune my car radio to the Hits FM or Fly FM or Mix FM's frequency at that particular situation, at that particular location. All right, so then only I can have and I can listen to Fly FM, Hits FM, or Mix FM, depending. Okay, so we must tune the frequency of the radio box or the radio at the car or our handphones so that it is actually in the same frequency as the frequency transmitted by the particular station. Okay, so that is the good effect. The second good effect is the loudness of the music produced by musical instruments such as the trumpet and the flute is actually a result of resonance in the air. Okay, this one I'm not going to emphasize much. I'm going to talk about this example that is inside the textbook. All right, this example comes from the textbook. Now, this activity, supposingly I wanted to do this activity, so let's see whether we have time or not to do after your exams. So this tuning fork, we will actually hit this tuning fork, and it is actually located above a box. This box is a hollow box. All right, this box is a hollow box with the opening at this part. This is the opening. Tuning fork Q is also located on the hollow box, and its opening is just facing at tuning fork P. Sorry. All right. So over here, when we actually hit, all right, we hit tuning fork P. All right, the vibration of the tuning fork will force the tuning fork at Q to vibrate in resonance with P's frequency. All right, the energy is transferred from this particular handle to the tuning fork, passing through this box, and the energy and the air particles, right, it will actually move and transfer the energy to Q. So when it turns to Q, Q will also start to vibrate. And when it vibrates, it will vibrate at its maximum amplitude and produces, ignore this, and produces a sound that is almost similar to P's frequency. Okay, so this is one example of resonance, good example. Another example is the Barton's pendulum. All right, so if you have the Barton's pendulum slide with you guys, please do make sure that you do put a remarks over here. All right, when they ask regarding resonance, they very famous ask two types of question. One is this Barton's pendulum. The other one would be the Tahoma bridge. Okay, so what happens when the pendulum X is made to oscillate? So before we actually explain all this, let's have a look at this whole setup. All right, this setup is actually a retort stand with P and Q is actually tied to a string, and then it will tie individual length of pendulums. Right, this pendulum, they do not share the same string. They are all individually tied. The only thing that is actually being shared by all this X, A, B, C, D, E, F pendulum is actually the string PQ. Okay, so what happens here is that this X will actually be forced to oscillate. Okay, so then the length of A, B, C, D, E, and F are different length. So when X starts to swing, it will actually oscillate. And when it's oscillate, it will actually cause the rest of the pendulum to oscillate as well. Why? Because they are connected to the line of PQ. So when X is being forced to oscillate, it will actually transfer the energy up to PQ, and then it will transfer each part of its energy down to every single pendulum. Okay, so here when it's actually all the other pendulum starts to swing, there is one particular pendulum will swing with maximum amplitude, which is actually pendulum D. Why pendulum D? All right, the main reason is because pendulum D has the same length as pendulum X. Even though pendulum X is bigger compared to the rest of the pendulum A to F, but because X and D has the same length of the pendulum, length of pendulum X and length of pendulum D is the same. Therefore, pendulum D will swing with the maximum amplitude. All right, the frequency of oscillation of pendulum X is equals to the frequency of oscillation for pendulum D. So the resonance has occurred at pendulum D and caused it to swing with maximum amplitude. So resonance happened between X and pendulum D. Okay, so this is actually the good effect of resonance. Now let's look at the bad effect. Okay, bad effect number one is the infamous Tahoma bridge. All right, in a short while, I'll show you guys the video, or I'll send a link to you guys later on. Now, Tahoma Bridge was a bridge that was built and it collapsed not long after that. Right? I think they only managed to use this Tahoma Bridge for less than half a year or 1 year, like that only. Main reason is because of they did not calculated the natural frequency of the bridge with the surrounding environment. Okay, we are not talking about the bridge to be swinging left and right. Okay, the main reason is when a strong wind comes and blow. The Homa Bridge is actually built in between two valleys. It's connecting two areas, and it's a big river underneath the Tahoma Bridge. So what happens here is wind always blow passing through this bridge. And when they blow a very strong wind blowing, it actually causes the bridge to vibrate at its natural frequency. So when it vibrates at its natural frequency, it will start vibrating at its maximum amplitude. It will actually starts to wobble. All right. And when the wind actually exceeded that natural frequency, the whole entire bridge collapsed. And thankfully, because they noticed that it's not really safe for the bridge, right? When the bridge really collapsed, no one was harmed, not even animals was harmed. Okay. So the second part of the bad effect of resonance is actually I think you guys seen movies before. When someone starts screaming or starts shouting, all right, and then the effect is all the window panels and all the glass, everything will start shattering. All right, that is actually the effect of resonance. Okay, explanation here: a soprano singer singing at frequency which is equals to the natural frequency of vibration of the glass, it will actually cause the glass to vibrate at its maximum amplitude. So when the soprano singer sings higher than the frequency, the glass will actually shatter. All right, the whole entire glass will actually break. So this is the bad effect of resonance. Okay, up to here. Any questions that you guys want to ask me? So far, okay? No question. I think should be okay, right? No response. And not Shock Sendiri explaining or disconnected already, right?
No, yeah, it's okay, Joe.
Thank you,
No,
Rabika. You're a
sure,
lifesaver.
but sure. Like, does it actually happen? You know, people singing so high that glass breaks. Does that actually happen? Oh,
Yes. Wait, ah. Give me one quick moment. Let me very quickly, while I'm trying to search for the video out, the rest of you, if you want to take a quick break, just go ahead and get a quick break first while I search for the video. You want- All right, so I'm going to share the video for the Tahoma Bridge and also the soprano part. So I'm going to share the video on the Tahoma Bridge first. I have a question. Does the natural frequency depends on its size? Not really. The natural frequency, I think it depends on many things. It can depend on the materials that is actually being built, the structure of the molecular structure, whether it's a solid, liquid, or gas, or how the situation is. So natural frequency has depends on many things. All right. So I'm gonna start sharing the video on the Tahoma Bridge first. Mm, yeah. Biggest problem of using MOE account. Want to share video also, I must share at the MOE tab.
As you can see, this bridge was exceptionally long and narrow, over half a mile long, only 39 feet wide. It lasted just 4 months. Tall, which were supposed to stiffen the bridge against bending. However, some up and down vibration was observed during the entire useful life of the bridge. Here's opening day. Natural modes of vibration, speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration with a period of 5 seconds.
Okay, I'm gonna fast forward a little bit.
A professor of engineering went out to see what had happened. He's coming back, walking with some difficulty
someone
along the
walking
nodal
here.
line, which is the center stripe of the roadway.
This is not animation, This is actually real life video.
It's remarkable that the girders were this flexible. This is photographed at normal speed. However, a collapse was inevitable after a little more than an hour of this.
You look at the vibration of the whole entire bridge. That is what it meant by maximum amplitude. And you can see that there's some structures that's starting to break already. So who's going to go into interior designer
The car
or
had been
architecture,
abandoned
make sure
earlier.
that
No
your
one was
physics
injured
are
in the whole affair.
good also.
However, a small dog in the car was frightened and was afraid to come out, and he perished along with the bridge.
Oh, I just know that. So this Tacoma Bridge is actually very, very famous in terms of resonance. All right, so that's the Tacoma Bridge. So they are saying that the main reason the Tacoma Bridge was it actually collapses because of the wind coming in was blowing so strong that it actually matches the natural frequency of the whole entire materials that made out of the bridge. So that's the reason why it actually collapsed. Now I have another video that I want to share with you guys, and that is answering Rabika's question just now. Okay, let's have a little advertisement first.
Shockwaves from a punch can do damage to the human body. Now we're going to time warp at 10,000 frames per second to see how sound waves destroy a glass. Jamie Vendera is famous for using the sound of his voice to destroy wine glasses. They seem to simply explode. But what's happening?
I know the sound waves broke the glass, but I couldn't see how. So I'm going to use our slow motion camera to see what we were missing. Instead of singing, I'm going to use a speaker and a tone generator. I have to find the natural vibrating frequency of the glass. I have to match this tone. That's it.
This is the exact tone to make this particular glass vibrate. When the tone is loud enough, the glass will shatter.
I can feel the glass shaking, but I can't see it. If I add a straw, then it's more obvious.
So what's happening here? The straw gets tossed side to side, but I can't see why.
Let's record it while I crank the volume.
You might want to lower down the volume of the headset now. Please do not attempt this at home.
All right, I took 10,000 frames per second, and I took 1 second. If I were to play back this whole video, it would take 8 minutes to get through.
Oh, this is amazing. What felt like the whole goblet vibrating is actually the rim bending back and forth, 337 times a second, the same rate as the sound waves. If I draw in the sound waves, you can see what's happening. One wave comes out of the speaker and pushes the side of the wine glass. The glass bounces back just when another sound wave pushes it again. If the timing or frequency of the sound waves is exactly right, the motion will build until the glass breaks.
Wow. So, as we would expect, the speaker breaks the glass nearest to it. And immediately we see a crack that goes all the way around the whole bottom of the frame. I'm going to play that back again. This is where the initial fracture happens, right nearby the speaker. And in about 3 frames, and this is 3/10,000ths of a second, we see this crack go along the bottom where the glass gets thicker and come right back up to the top where it's thin. So if we follow that a little more, this piece has just fallen off, but it doesn't in some sense even know that it's fallen off from the rest of the glass. All of the glass was shaking at about 300 hertz, 300 vibrations per second. And this piece is still doing that. You can see the corners of the glass still flexing as if they were influenced by the speaker, but the speaker is way too far away now to have that influence on this piece. It just has the leftover inertia. And we see that in all the pieces here, even along the top edge of this glass. This piece of glass is not resonant at that frequency anymore, so it can't get energy from the speaker. And all that we see shaking is the leftover energy from what the speaker gave it in order for it to break.
So, if you thought that glass couldn't bend, think again. Time warping changes the way we see the world because it makes the invisible visible.
What?
Okay. Hwayong's question, what if the wave comes from every angle? There are actually videos on this already. Whatever that you guys are trying to think of, the question, if I'm not wrong, it has been actually taught by many other peoples, but this video has been recorded with precautions, and it's actually all the safety precautions is there. You saw the guy actually wear the protective goggles. All right, so please don't attempt this by yourself, and please kindly do not take your mom or your dad's wine glass to actually attempt it over Christmas. Okay, so let me close this and get back to here. Okay, so I'm gonna get back to here. All right, this exercises, it's still not class point yet because I just want to discuss with all of you, and I want to let you guys see how I answer these questions that I took from the previous syllabus last time. So it's still applicable for you guys. Okay, so in this question, it says the figure shows a simple pendulum with a mass of 40 gram with a length of 20 centimeter. Pendulum makes 20 complete oscillation in 18.8 seconds. So the relationship between the period of oscillation T and the simple pendulum is expressed in the formula below. All right, so what is this? Excuse me. All right. Apa yang tengah berlaku ni? Did my... Okay. All right. So here, using the letters A, B, and C from the figure, state the equilibrium position. Okay, so equilibrium position means the resting position for a pendulum. So resting position for a pendulum is definitely vertical. So the question just asks you to state using the letters A, B, and C from the figure, state the equilibrium position. So the position is definitely B. Just simple as that, you'll get 1 mark straight. The order of position of the pendulum in a complete oscillation. Now, complete oscillation means, if you were to recall in your experiment for a paper tree, all right, it is actually moving from one end to another end. So in this case, you can actually start from C, B, moving to A, and then it goes back to B and back to C again. So you can also answer starting from A to B to C, and then back to B and A again. Can, no problem. Okay, you can also say that you start from position B. If you start from position B, it can goes to A, back to B, to C, and then back to B again. All right, so any other method, as long as one complete oscillation, the answer will be acceptable. So please make sure that you write the arrows. Okay, so that's the first part. Now, second part. All right, again, this question is me trying to explain, so I'm not going to take out the class point yet. So I'm still going to explain this question due to the time. So here, question asks to calculate the period of oscillation for the pendulum. Here it says that the pendulum took 20 complete oscillations in 18.8 seconds. So the time small t is 18.8 seconds, but it took 20 complete oscillation. So the period of the oscillation capital T is the small t divided by 20 oscillation. That would be 18.8 divided by 20. Okay, I just noticed my calculator not with me. Right, give me 1 quick minute. Cross-check my answer also, because I'm using my handphone. So that would be 0.94 seconds. All right, so if I calculate wrongly, please do let me know. Now, then the question asks, what is the frequency of oscillation of pendulum? This one can use the wave question. Main reason because the pendulum is undergoing oscillation. All right. A wave is a transfer of energy without transferring matter due to an oscillation or vibrating source. So the pendulum is oscillating, that's why it's considered as a wave as well. Now, what is the frequency? Frequency formula is 1 over period, so that would be 1 over 0.94. Okay, so let's see. 1 divided by 0.94, I get my answer to be 1.06 hertz. Or you can also write it as 1.06 second negative 1. All right, so that is the frequency of the pendulum. Okay, so I hope you guys are okay while you're copying the answers down.
Sure. If you do question B with the formula they gave, the T equals 2 pi square root L over G, that's also okay, right?
You don't have G.
Oh, I assumed it was 9.81.
Why want to use that formula when they already give you the time
Because they
taken for
gave us
20
the
oscillation?
formula, Che.
Why want to go in trouble? Yeah, but the formula doesn't have to be question B, ma. The formula is actually for the next question.
For question C?
You can actually do that. It's for D if I'm not wrong.
Oh, E. It's for E. Yeah. Yeah, I did it for E.
So because the question is already given there, you can actually try to calculate. Technically, if they check the answer correctly, the answer for period should be the same. But then you would spend a lot of time, lah.
I got 0.89 seconds.
So for me, it's actually based back on the question. All right, because this is a practice question, so maybe they didn't get a second teacher to actually cross-check the working and the questions. Technically, it should be able to get back the same answers, lah. All right, so I'm going to go to question D. What happens to the frequency of the pendulum when the pendulum bob with a mass of 50 grams is being used? You see that this is actually quite a long question because this is supposed to be 2-mark question. Okay. Okay, sorry. Too many guests today. Now, what happens to the frequency? Here, Alright, this is the formula to calculate the period. And then the frequency formula is actually 1 over t. When you change the pendulum bob with a mass of 50 gram, which means you increase the mass, actually nothing will happen to the frequency. So what happens to the frequency? No change. Alright, no change to the frequency. And because I know this is a 2-mark question, reason is because I didn't screenshot out the markings over there. All right. So I need to explain the reason. Reason is because mass does not affect the frequency of the pendulum. Okay. Then the question asks, determine the frequency of the pendulum when the length of the pendulum L is increased to 80 centimeter. So over here, then only we use the formula T equals to 2 pi. All right. Square root of 80 centimeter, I have to change that to meter already. So that would be 0.8 over 9.81. Okay. So let's see. Please again cross-check the answer. I'm using my handphone, which I don't think so is as accurate as the scientific calculator. 0.8 divided 9.81. 2 pi square root of 0.0815. You can use pi as 3.142. You can actually use the pi symbol. Answer will still be okay. Still be acceptable. So I got my period to be 1.791. This is in second. But the questions wants frequency. So frequency is 1 over period. So I have to inverse my question right now. 1 divided by 1.791. So my frequency right now, I get 0.558 hertz. So do cross-check my answer and see whether my answer and yours is the same or not. Rabika, did you get the same answer?
I actually forgot to get frequency, but it's 0.56.
Okay,
0.56.
acceptable.
Okay.
Acceptable. 2 decimal places or maximum 3 decimal places, as long as the unit is correct. All right, so the rest of you, please copy this down or screenshot this down because I'm going to go to the next slide already. Okay, so that is a question on wave lah. Okay. All right. After oscillating number of times, the pendulum will finally stop. Why? Okay, so the pendulum will definitely stop because of damping. You can actually use damping. You can actually say loss of energy. All right. You can also say due to internal or external damping. All answers is going to be acceptable. All right. Then sketch a displacement time graph to show the oscillation of the pendulum until it stops. So here, use back the picture that the picture that we had just now. All right, and try to sketch or try to show me your oscillation. Okay, I want to see your graph of the damping graph that you draw just now together. So number 1, please enter class point. Because after this also during reflection of wave, we will also discuss some questions already. Hi, is anyone entering class point? Thank you, Audrey. So those who entered class points already, you can actually screenshot the picture of the damping graph that you draw just now. So I just want to cross-check and check how did you guys draw your displacement time graph or your amplitude time graph just now. The y-axis should be displacement, not amplitude. My bad. So can you change the y-axis? Please change the y-axis from the amplitude to displacement. All right, and then take a picture of your damping graph that you draw with me together just now and just send it up so that I can actually look at your graph. Thank you, Rebecca.
Wait, Cher, can you check if the photo is clear? Okay.
Yep.
Thanks, Cher.
Good. Thanks, Sue. Yes, you can use the one that you did just now. I just want to see how did you guys actually draw just now. If you have already drawn from this question also, you can actually send that to me. I just want to cross-check and to show and discuss with all of you how the graph is supposed to be drawn. Thank you, Ray. The rest of you, try not to be so shy in sharing your answers, okay? It's better for me to identify and to guide you on which is correct and wrong in class better than in exam. So I'm waiting for another 2 more graphs, then I'm going to discuss it. Anyone else want to submit their graph? Thank you, Adelia. Okay. All right, I'm going to close submission for now. I'm going to use that to discuss the answer. Okay, so let's have a look at all this graph. Okay, we have Rebecca's graph. So you have displacement time, amplitude, negative A. All right, there's the 0 over there. So you have the dotted line and then you have drawn the graph. So, okay. Rebecca's graph is okay. Sorry, too many guests today. Okay, then we have Chirong's one. Chirong, please can you change this to displacement? Sorry, was my bad just now. This is supposed to be displacement. And even though we do not know what's the unit, just put it as M at the top part. The rest of you also, if you copied amplitude just now, can you please kindly change to displacement? Erica, I'm not very quite sure if I get your submission, so I'll see in a short while. Okay, so that's negative, that's 10. Chirong, please put a 0 over here and make sure there's a negative in front of the 10 at the bottom part. I couldn't see whether there's a negative sign or not. Graph-wise, amplitude decreasing, but please do one thing in the exam, try not to sketch like this. All right, try to make a very nice curve as much as you can. All right, but anyhow, this will be acceptable, except for one question. How come this graph over here so weird one? All right, Chirong, so please take note, All right, so we have Adelia's graph, amplitude, again, change to displacement. Okay, 10, 0, negative 10. Amplitude decreasing. Okay, good. All right, let's go next. We have Xinyan's graph, Displacement, okay. Xinyan, please put a 0 here. Amplitude wise, okay, Xinyan, for your graph, right, it is better that you curve down some more. All right, let it curve down some more because this part looks like it's almost the same amplitude. All right, Xinyan. Okay, let's go to next. This is Ray's graph. Ray's one also, Ray, how come your decreasing amplitude looks so weird? Your decreasing amplitude is supposed to go down like this. Okay, so be very careful, huh? The labeling wise and all that's correct. It's just the curve there only, okay? I have Brian's one here. Displacement. Okay. Brian also the same thing. This one doesn't look like it's undergoing damping. Alright, it needs to go downwards some more. Approaching 0 but doesn't touch 0. So Erica, I did not receive your answer, Erica. Sorry. Okay, state what type of energy of the pendulum when it's located at B. B is actually at vertically downwards, so that is gravitational potential energy. Alright, the energy is gravitational potential energy. Hey, wait, Chop, salah. Puan Leong pun salah. B is actually at the lowest position, where C is actually at the maximum position. So B is supposed to be kinetic energy. C is actually at a higher position, so it has a height, therefore it possesses gravitational potential energy. You write potential energy only, also acceptable. Gravitational potential energy is a more accurate answer. Alright, between C and
Sure.
B and C would be, yes.
If the pendulum is at B, like if
Mm.
if the pendulum is at B, even if it's not moving, wouldn't it still have potential energy?
Yep, it will. But right now they assume that it's actually oscillating.
Oh, okay, okay.
Mm.
So if you write potential energy is wrong, is it?
Mm.
Oh,
For this question.
okay, thanks, sure.
Alright, so that is the answer for this question. Okay, up to here so far, I think the next slide is actually going to reflection of wave already. Okay, so those who's writing the answer, screenshot this. Whenever actually I use class pointer, you all enter class point already. Actually, you all can save the picture already, you know. Alright, I'm gonna proceed to the next slide already. Alright, we're gonna talk about reflection of wave. Reflection means pantolan, to bounce back. Alright, reflection actually means pantolan. Alright, reflection means to bounce back. Okay, so over here, when wave is traveling, alright, when it reaches an obstacle, the wave actually gets bounced back. Sorry, let me silence my phone first. Okay, so over here, what you can see is that the wave is moving towards the right hand side, and then there is a plane reflector. So the wave will actually bounce back to this side. Okay, or whenever you go to the seaside, all right, the wave that comes in from the sea, when it actually hits the wall, it actually gets bounced back. So this wave are the bouncing back wave. That's the reflected wave. Okay, don't learn from me, keep on saying the word bouncing back. All right, the reflected wave. Okay, so that is actually reflection. Now, when we talk about when we start talking about this, okay, I'm gonna start scribbling on the whiteboard first. Mana saya punya marker? Okay, I'm gonna start scribbling something first. There are 4 phenomena that is being mentioned, a part of resonance and damping. Okay, there's 4 phenomena that we're gonna learn. The first phenomena that we're gonna learn is about reflection. All right, reflection of wave, then we're going to learn about refraction of wave. This too you have learned previously regarding using light wave back in chapter Form 1, if I'm not wrong, Form 1 or Form 2. All right. Then after that, we will learn about diffraction. And then we will learn about interference. Okay, whenever we talk about this four phenomena, we will actually focus on in this chapter, I noticed they focus more on water waves and also sound wave for reflection and refraction, because in chapter 6 we will focus on reflection of light and refraction of light. So light is also a type of wave, but they took out from this chapter to talk about it in the next chapter. Diffraction, we will talk about 3: water, sound, and light. Wave interference also, we will talk about 3: water, light, and also sound wave. All right, so the few characteristic that you guys have to be aware of is the characteristic where, let me erase everything. Okay, we have to talk about a few characteristic. First is we have to talk about the frequency. Okay, then we will talk about the period. We will talk about the wavelength. We will talk about the wave speed. Sometimes they talk about the amplitude. All right, so these are a few things that we need to emphasize. And one more thing that we're going to talk about is actually the direction of the wave. Okay, so you need to know what is the cause and what is effect. So if the frequency, what can change the frequency? I just noticed I spelled frequency wrongly. What can change this characteristic? All right, the thing that can change frequency is actually the source of the vibration, the source of the wave, the thing that is oscillating. So if the source of the vibration changes, it actually changes the frequency. What changes period? Obviously one thing more, frequency ma, because their formula is F equals to 1 over T. All right, if the frequency change, the period will change. Okay, so what will cause wavelength to change? The medium that is propagating. All right, if we are talking about light, then it will be the optical density. Okay, those who have already learned chapter 6. If we are talking about water wave, all right, then the one that will change is actually the depth of the water. Can I ask, is my screen okay? Suddenly feel like my tablet hang already. Okay, then if you're talking about sound, then it would be the air's density or the temperature. Okay, so these are actually some of the characteristic of the medium that will actually change the wavelength. Then wave speed formula is V equals to F lambda. So what can cause the wave speed to change? That would be the frequency, the wavelength, or the period. All right, wave speed will change because of the frequency. All right, the wavelength, and also period of oscillation. Okay, the amplitude sometimes it's being mentioned. Normally amplitude is actually related to the energy. Okay, and finally direction. This one it depends, like if there's an obstacle or there is something that's blocking it, then the wave will definitely change. All right, so these are the things that you have to take note when you do analysis on questions regarding wave. All right, so I'm going to start with the explanation for reflection of wave. All right, so reflection of wave, the effect, the characteristic of the wave. So for reflection of wave, it actually means that when a wave comes, it's being blocked by a reflective surface. All right, it can be a wall, it can be a mirror if it's light. All right, if it's sound, most of the time it's going to be a wall anyway. So when it hits the wall, does the surrounding changes or not? Okay, so you have to look back at this. When a wave hits a wall, does the source change? If the source doesn't change, the frequency will not change. All right, if the frequency doesn't change, the period doesn't change. Okay, then look at the medium. When the wave hits an obstacle, does the medium change before and after it hits the obstacle? If the medium doesn't change, the wavelength will not change. All right, if the frequency doesn't change, wavelength doesn't change, the period doesn't change, so the wave speed will remains the same. And then amplitude, does the energy loses? In ideal case, energy doesn't lose. Okay, but what will change? The direction definitely change because it reached an obstacle. So over here, the effect of reflection and the characteristic of wave, first is the angle of incidence. Because this is reflection, it will have to obey the law of reflection that you learn in Form 1. All right, law of reflection states that the normal line, the incident ray, all right, the incident ray, the reflected ray, all lies on the same plane. All right, are on the same plane, which means the same axis, y-axis, x-axis. All right, and the second law of reflection states that the angle of incidence is equals to the angle of reflection. All right, that is the law of reflection. Okay, so here angle of incidence and angle of reflection needs to be the same. All right, because it needs to obey the law of reflection. Then the wavelength, the medium doesn't change. All right, if let's just say I am in a room right now, if there is no cushion, there is no bed, there is no curtains around, it's just an empty room. And when I teach in this room, I will hear echo. That is because my sound is being reflected back. But the wavelength will not change because I'm still in the same room. The temperature doesn't change, the medium doesn't change. So there will be no change in wavelength. Okay, next is the frequency. Frequency depends on the source. So even though that it hits an obstacle, the source, which is me, doesn't change at all. All right, so the frequency will not change here. Next is wave speed. Wave speed formula is V equals to F lambda. Okay, so if the frequency doesn't change, the wavelength doesn't change, therefore wave speed also no change. So what changes? The direction of the propagation. The wave initially moving towards the right, when it hits a wall, it will actually move towards the left, right? Because it's being reflected back. So the changes with the condition that the angle of incidence is the same as the angle of reflection. So this is the characteristic of reflection of wave. Okay, so how to draw? All right, this is similar of drawing your ray diagram in Form 1 actually. Okay, so if there's a plane mirror over here, this is the incident wave. All right, first step, draw a narrow line AB perpendicular to the incident. So I'm going to draw a normal line perpendicular to the plane. All right, then you draw the arrow towards that point. Okay, the wavelength, the blue color lines are wavefronts. These blue color lines are actually wavefronts. If you recall the first part that we learned when we talk about wave, this is a plane wavefronts. All right, And then the distance between the two wavefront lines, they are supposed to be the same. Why? Because they represent wavelength. All right, so the wavelength doesn't change because the medium doesn't change. So you need to make sure that you draw the same distance between each line. Then after that, measure the angle of the incident and measure the angle of the reflection and bounce it back up. So if the incident angle is 30 degrees, then the reflected angle should be 30 degrees as well. Draw the arrow, all right, and then measure the wavefronts again. So normally I use 0.5 centimeter. All right, when I draw in an exam, I usually use 0.5 centimeter or 0.2 centimeter. It doesn't matter for reflection of wave. As long as the distance between the two lines are the same, it's acceptable. Okay, so I notice my line is starting to get that already. Okay, so this is actually drawing the reflection of wave. They seldom ask to draw in wave, all right? They normally ask all the complicated questions in wave. Okay, now what are the applications? Do you mind if I drag a little bit to finish up the applications for reflection? I won't drag until 10:30, don't worry. The most is another 15 minutes only. Okay. All right. So the applications of reflection of wave in daily life. The phenomena of reflection can be applied in our daily life for a few situations. The first is actually ultrasonic wave, all right, that is used in the medical field to examine the fetus or the other internal organs using the ultrasound. Okay, so here, as you can see, this is a career, right? This is Officer of Science of Physics. They are actually mainly used to do ultrasounds. All right, I do have a friend who actually just he learned everything about the ultrasound, and his only task is actually to do ultrasound on patients only. Okay, so here, all right, this is actually ultrasound wave. I'm just going to explain this because I had this slide from my previous syllabus notes. Okay, so application of reflection of sound wave. Now, sound wave, we actually have two types of wave. We have ultrasound and one more is ultrasound. The other one is, I need to check back my old syllabus already. Sound, there's two category: very high pitch and very low pitch. High pitch corresponds to high frequency. All right, so ultrasound is actually somewhere higher, if I'm not wrong. Okay, ultrasounds is used to scan and capture image of the fetus in a mother's womb and the image of the internal organs. All right, so this picture is actually the sonogram effect from the baby featuring. So how does this happen? Transmitter P, all right, it will actually send a single signal, one single of ultrasound moving downwards towards the baby. All right, when it hits the baby, it will actually bounce back up and to be detected by the detector. All right, so this is actually reflection occurring. All right, this is application for reflection. And once it has already detected, all right, the soft tissue of the fetus will absorb most of the incident ultrasound and reflect very little. So as you can see over here, the soft tissue actually is being absorbed. So it's being reflected very little. The bony parts will absorb very little, but reflect most of the ultrasound. So don't worry about these 2 points, okay? So the reflected ultrasound will produce an image of contrasting brightness. So from the reflected ultrasound wave, that is actually how they detect whether the baby features is good or not and everything. Okay, so we're talking about the normal sonogram. So what other applications of reflection is there? All right, next application is radio wave from telecommunication satellites. So telecommunication satellites is whereby, let's just say at Bukit Jalil, we're talking about Astro. All right, Astro, they have a satellite dish, okay, that will send a signal up to the satellite. All right, they will send a signal up to the satellite. And then after that, the satellite will send the signal down back to our house. All right, so the wave that they send for communications to satellites, they are actually radio wave. In the last subtopic, we will learn about electromagnetic wave. All right, so For sonogram, right, to detect fetus, they actually use ultrasound wave. For telecommunication, we use radio waves. Okay, so and then just to quickly inform to you guys, all right, normally when you see this satellite dish, it will be a concave surface. All right, concave surface whereby the incident wave, when it comes, it will actually get reflected back onto this signal, this particular receiver. This is the receiver part. All right, and this receiver distance from the center of the curve to the receiver distance, this is actually the focal point, the focal length. All right, the receiver is actually located at the focal length of this particular satellite dish. The satellite dish main purpose is actually to reflect the wave only. Okay, so then after that, what other applications? This is actually the radar. All right, this is a for ultrasonic reflection as well, known as the sonar. Okay, whereby a transmission, the transmitter will actually send a single ultrasonic pulse wave down towards the sea, and then when it hits the seabed or it hits the fishes, it will actually bounce back up. So from there, that is actually how they detected whether that location got fish or not, whether that location got other submarines or not. And then those, when we watch the movies, they will always have the beep beep sound. That is actually the sonar. They are actually sending wave out to be reflected back to determine whether that position is far or low. Is there fishes underneath there, or is there coral reefs over there? All right, that is actually the main purpose of the sonar. And then after that, another one, this one is also for the seabed. All right, patterns of reflected sound wave caused by different rocks enables the location, depth, and structure of the seabed, which contains sources of natural gas, to be identified. Again, they actually send the wave down, all right, and then it will bounce back up. Okay, so the next part that we're going to talk about is the you don't really, this whole entire part, just let's see, sonar. Okay, maybe very quickly I can mention this lah. Alright, sonar, the sound navigation and ranging, is actually used to locate underwater objects to measure the depth of a seabed. So ultrasonic wave, which means the frequency greater than 20,000 hertz, which we humans cannot hear. Alright, we all humans can hear until, if I'm not wrong, 2,000 plus, and that is actually very, very high already. Okay, so over here, the ultrasonic wave emits from the transmitter and reflect the objects on the seabed. So then it is reflected, the reflected wave will be detected by the receiver. What do they calculate? They calculate the time interval, all right, between the wave being emitted and received. So if the speed of sound wave is known, all right, normally it's around 330 meter per second, then they can actually calculate how deep is it. So I'm gonna show this out by showing this to you. Okay, so let's just say one thing. This is the sheep. All right, so let's just say there's a coral down here. Okay, so the ship will actually send a single pulse of wave traveling down. All right, at a wave speed of v. All right, the wave is actually traveling down. So what they do is, when they send this wave, the time is actually 0 second. When the wave traveled downwards, it would have already traveled a depth of d. Then once it hits the coral, it will be reflected back up to the receiver, and they receive it as time t seconds. So this wave would have already traveled down a depth of d, and it travels up back another depth of d. It moves at a wave speed of v. So here, what do we do? Speed. All right. Speed is actually distance over time. So when the sound wave traveled a distance of 2d, because it went down and it came back up 2d, the total time taken from the transmitter sending out the wave until it receives is actually time t. So that is divided by t, and it travels at the speed of sound, which is v. All right, so that is how we got v equals 2d over t from the formula of speed equals to distance over time. So that's why sometimes they said if I want to calculate the depth would be actually vt over 2. Right, that is how they rearrange and get the formula back. Okay, up to here, are you guys all right?
Yep. Okay, Cher.
Okay, yeah. All right. I think this is okay. I can't really continue already. My girls are actually calling me outside. So what I want you guys to do is to try this question first using the formula that I just gave. All right. So then also try this question. Then we will discuss it the next lesson, is if that's okay with all of you. Let me unshare. Okay, so I hope that I actually with that slide in terms of reflection of wave